And similarly, in large buildings or in typical buildings that we design in India, what we have is a lot of infill walls that's used to cover as partition walls, and which are not so great in earthquake. And these infill walls sort of act as a compression strut in a building. So when the building moves, these infill walls are very rigid and doesn't have a lot of ductility, so a lot of cracks will be formed, and there is a lot of collapse of infill walls that will actually be damaging, uh, as you can see in a lot of earthquakes. So for RC buildings, if you can summarize, then this is the picture that tells the story very well. What you want is strong columns and weak beams, not a weak column and strong beams. The philosophy of this is that you have to distribute your damage all throughout the height of the building, mostly in beams, because if a beam suffers a damage, like it is localized in nature, but if a column suffers a damage, then it can take down the whole building. So, so your philosophy in reinforced concrete design is to have strong columns and weak beams, and not to have the plastic hinge, or not to concentrate your damage at one story or at the columns. Try to distribute the force throughout the structure so it performs ductile as well as doesn't collapse at a single instant. And here are some very good pictures from the IS 13920 code, showing what are the good detailing practices in beams. So for gravity, although a beam may act very well if you have designed the beam for gravity, but in earthquake, you have to keep in mind some of these clauses so that the beam uh, doesn't collapse in a large earthquake. So to understand the good detailing practice in beams, what you have to know is that you have to provide a lot of closely spaced ties around the column of the building of the beam. So you may have spacing of the stirrups that is wide at the center, but at the end where you have large forces at the sides of the columns, let's say about the distance 2d from the face of the column, you have to provide closely spaced stirrups. And also these stirrups has to be provided with 135-degree hook at this inside, and these hooks should have a 10 times of the diameter of the stirrup. Similarly for columns, we have to provide vertical ties that we saw in beams as well. So you have to provide a 135-degree hook, bend it on the inside, provide at least 10 times the diameter of the tie. Uh, and and the reason for this is like we don't want the failure that we can see over here. Like we don't want failure where you don't have sufficient ties or you don't have sufficient hooks that's going to prevent the failure of the column. So you have to tie that very well with this sort of requirements. And if you have a large column with multiple longitudinal bars, then you have to provide extra links at the center as well. The links can be 180-degree links, or it can be 135-degree ties. And if you see a column in the vertical elevation, so what you should note is that the regions of the high force, which is the area near the beams in the columns, has to be provided with a very closely spaced ties. And you also have to keep in mind about the lapping of the vertical bars in the center of the column, so you cannot lap at the junction of the beam and column, because that would just try to separate it when a large earthquake happens. And for normal buildings which doesn't have a shear wall or any sort of other lateral load system, what we have is just the beam and column as our lateral load resisting system. And in that, the beam column joint, as you can imagine, is a very critical portion of the building. So no matter how ductile or how strong your beam and column is, if you don't have a very good beam column joint, then the failure happens there, because it is the area where a large amount of force has to be registered. So the IS 13920 code again lists some of the requirements of the beam column joint and how you can use ties to actually confine this space. Now going back to the layout of the building, open ground story, which we can see normally all over large metro cities in India. These are very economical for the builders because this provides a large parking space at the ground level, but then you have a huge mass concentrated at the top of the building. And this is not a great layout for earthquake. As you can imagine, this sort of acts like an inverted pendulum, which has a large mass at the top. So when the earthquake happens, this pendulum kinds of vibrates very rapidly, and that is not a good situation, because then you'll have uneven distribution of the stiffness. You have a large stiffer upper stories, but then you have a very low stiff lower ground story. So you have large displacements, and then you have to register a large amount of force. So in regions of very high severity in zones 4 and zone 5, when you have a typically large buildings, um, it's very difficult to work with beam and column as a lateral load racing system, because in a very high seismic zone, you may be able to satisfy your force requirement, but when you have a beam column joint, then you may find it difficult to resist your deformation requirement. So your building may displace a lot in those higher severity zones. So to prevent that, normally you'd have a shear wall uh, throughout the length of the building. This is also typical in buildings with elevators where you have a confined space of an elevator, then you can provide shear walls around that elevator. But keep in mind that when you provide a shear wall, then you have to follow symmetry. If you have a very unsymmetric location of shear walls in the building, then the building kind of twists because you have a stiff part at the left side of the building, but then you have a very open part at the right of the building. So the building kind of tries to twist. So there's an uneven distribution of the stiffness and uneven distribution of the force. A good layout is the one shown over here in green. So you have like equally spaced shear walls. The shear walls are equal in length, distributed symmetrically on both axes of the building. So this is a very good layout to follow when you are trying to design with a shear wall structure. To understand what is a shear wall and how it acts, so when you have a shear wall, so this is the elevation of the shear wall over here. When you have a earthquake force acting on the left, or you can imagine from the right as well. Let's say when you have earthquake force here, then you have a tension on the left side of the shear wall, and then you have a compression at the right, and then this reverses in each instant of the earthquake. So the zones in the end, the left and right, has to be detailed very well. It is referred to as a boundary element in the code. So if I cut a section here, these boundary elements has to be designed similar to a column. So you can imagine there is two different columns at the end of the shear wall, and then you have distributed vertical and horizontal bars at the center. So these boundary elements are very critical in resisting that tension and compression at the end. Um, you may also provide these boundary elements with a larger thickness at the end. Um, so, so this is like a very good detailing practice to have a confined zone with the closely spaced ties at the end, and then you have a very good lateral load resisting system. So to summarize, what are the load paths and why it is important? So you have a building, but in a building, as you can imagine, mostly all the floor mass, all the mass of the building is concentrated at the floor. So you have a large mass of building at each story levels, and then you have columns or shear walls as your lateral load resisting system. So you should have a very good load path from the floor to the foundation. If you don't have a very good load path, then if you have some weak joint in a building, whether it is a joint of the shear wall or foundation, or whether it is a beam column joint, then that is the point of failure. So you should understand that earthquake design is not just designing individual component, but looking at it holistically and seeing that when you have inertia force at the floor of the building, then whether you can transfer that inertia force very well to the foundation or not. So I'll now start with the wind loads, which is another important dynamic loading in the building. And we know like what is a wind load, right? Like it's a very large, a very high speed wind force acting on a structure, and it is more severe in different regions of the world than all the regions of the world. And also it's unpredictable. So although not fully unpredictable like earthquake, we have a lot of weather forecasts these days that can accurately predict wind so that people can be evacuated easily before that major event happens. But the structure, you cannot move from one place to another. You can move people, but not the structure. So your structure is going to suffer the damage if you don't design your structure for that wind load. There are different categories to define wind, but the most accepted is the Beaufort scale, which sort of lists your wind category from 0 to 12. So as you can imagine, 0 or a low category is nothing but a light breeze or a moderate breeze up to 20 to 28 kilometers per hour wind. But a large category is the ones such as storm or hurricane, which can be up to 120 kilometers per hour. So what does a wind force do to a building? So when you have a wind force acting from any side of the building, you have a positive pressure on the surface that it is facing the wind. So you have a lot of force on the face that the wind acts. But then also you have suction on the rear wall, which you also call as negative pressure. And then once there are windows or in sort of openings in the building, the wind goes inside of the building as well, and then it tries to push the side walls as well, which are basically another sort of suctions on the sidewall. And then you have the uplift on the roof. So imagine wind acting on the face of the building. It doesn't just cause damage to that face. It sort of tries to uplift the roof. It tries to tear out your rear wall as well, or it tries to damage your side walls as well. So it's acting on the whole of the structure and not just on the face of the wind. And most of the people think that wind is a small force. No, it is not. It is a very large force. As you can imagine, in regions of high wind force in coastal regions, there is a lot of uh, irreparable damage to the buildings as well, but also a lot of facade elements. So you don't see these kind of damages a lot in other regions, but in coastal regions, if you have a high-rise building with a lot of glass facades or a weak cladding element, then a wind can damage that a lot, and it can be damaging to the people as well. You can have a lot of casualties from wind. And IS 875 Part 3, which was updated in 2015, is the latest Indian standard that you have to follow for design loading for wind on a building structure. So what this code gives is it gives you the forces, and it also gives you methods to analyze. Similar to earthquake, you can analyze this as a linear static or a linear dynamic method, depending on what you are or what you are designing. We'll talk that in a little bit later, but keep in mind that wind can also be designed in static and dynamic method. And then what this code gives basically is it gives you a design wind speed, which is basically a formula over here. You have to figure out your basic wind speed depending on where you are designing, and then you have different factors from K1 to K4, which is used to multiply your basic wind speed, and then you get your design wind speed. Similar to your seismic zone map, we also have a basic wind map for India. If you follow any other code, then you can find similar wind maps as well. So what it does is it records wind all over these areas and averages it over a length of time. So you get like a basic wind speed that's supposed to act on the structure that you're designing to. So although it's not very clear, but all these regions in blue and pink are the regions of high wind speed. So anywhere in red or blue may not be that significant, but all these coastal regions, as you can see, all the coastal region in the east of India and the coastal region on the west of India, the areas around Gujarat and Maharashtra, and then Leh and Ladakh and some portions in the northeast as well, have a very high probability of high wind speed. This is also summarized in the table in the code. As you can see, this was averaged at 10-meter height at different cities. So if you don't find your city, you can sort of like look for the city closest to your city that you are designing and use that wind speed. So typically most of the wind speed, the high wind speed are generally about 50 meters per second. The low wind speeds are about 30 to 39 meters per second. And to talk about the factors that's going to multiply your wind speed, the first one is K1 factor, which is the probability factor. So it is nothing but like depending on what you are designing and where you are designing, you have these different factors to multiply. So if you are designing a temporary site, or if you are designing an important building, your factor changes, and also your design life of the structure, whether it is a temporary site or an important building with a 100-year life, you have different basic wind speed K1 factor that you can use. So if you are designing a very important building with a high wind speed, then you have a higher factor. But if you are designing a temporary site in a very low wind speed, then you have a lower, in case you are like reducing your design wind speed. The second factor, K2 factor, accounts for your terrain height and the size of the structure. So what it does is divides your location into 4 different categories. First category is you have just your structure and nothing around it, so there is no obstruction. The second one is you have few obstructions with trees, some grassed areas, and heights up to 1.5 to 10 meters trees. And then you have the final category, category 4, as you can imagine in large cities where you have a lot of obstructions. So depending on where you are located, it has a different K2 value that you can use. So this is your height of the structure, and depending on where you are in terms of the exposure category, you have different factors to multiply. The third one is the topography factor. It is going to take into account your site of the building, where you are located at the hill and ridge, or whether you are located at the cliff, because these sort of features in your topography will change your wind speed. It's not like a flat ground where you have a basic wind speed. The wind speed will change depending on where you are located. If you are at the high of a crest or at the edge of the cliff. These are some nice charts that will help you depending on your height of the building, depending on whether you are upwind or downwind. You can find different K3 values. And then the final K4 value is for the cyclonic effect. For most regions of India, you don't have to worry about that. You'll fall into category as all other structures with a K4 value of 1. But for areas where you have a high probability of cyclonic wind, most of the east coast of India and some of the west coast of Gujarat, you have a high K4 value that you have to multiply. Cyclones are basically wind which are very high in speed and cover large areas up to 60 kilometers of width at a time and are very damaging. And once you found out your basic wind speed, then you have to calculate your design wind pressure. So there are different formulas to calculate that. So you have to find your wind pressure PZ at any height of the building. And then once you have found out your PZ, then you have to again find your design wind pressure. So this is the value that you are going to use to design your structure, which also has some multiplication factors, KD, KA, and KC, which I'm going to talk about now. So KD is the wind directionality factor. So depending on whether you have a building with a large surface area, or whether you have a circular building, or whether you have different tributary areas that's exposed to wind, you have different KD factors. And then the second factor, KC factor, takes into account of different combination effect of the wind. It's not just the wind acting on one side, it takes into account of different combined effect of windward and leeward, or positive and negative pressures. So you have this KC factor that you have to follow as well. And then you have the dynamic effects of the wind. So once you have calculated your basic wind speed with static wind procedures, the code also says that wind is a dynamic phenomenon. So you also have to consider this if you are designing something irregular, or if you are designing something very tall. Basically, the requirement for dynamic analysis is summarized as buildings and any structure with height to minimum lateral dimension of more than 5, and buildings which has a natural frequency less than 1 Hz. So any sort of tall buildings or a building with a height with a dimension of more than 5, you have to do a dynamic analysis. So similar to earthquake, you also have different formulas to calculate the fundamental time period of the building, depending on the height of the building, number of stories, and the lateral dimension of the building. You have 2 different formulas that you can find out your fundamental time period. So to understand the dynamic effects, why it is needed. So for a simple small building, it may be okay to do a static analysis. For a large tall building, it may not be okay just to follow the static wind procedures, because wind is a dynamic effect. So when you have a wind acting on a tall building, the fluctuation of the wind is not uniform throughout the height of the building and throughout the width of the building as well. So you may have a 50 meters per second wind at 10 meter of the building, but if you are designing something 60 meter in height, then the wind speed will vary at the top of the building. And also you'll have resonant vibrations. So if your fundamental period of the building matches with that of the wind, the 2 vibrations will combine to create a greater amplitude, which is known as resonance, and it can be damaging as well. And then the third important phenomena is the vortex setting phenomena. What it does is, if you have a wind load acting on the face of the building not just displaces on that side of the wind, but it also tries to fluctuate on the across wind, the perpendicular direction, and then that creates a phenomena known as vortex setting around the sides of the building. So these are the different dynamic effects that you have to take into account. So after wind and earthquake, so you may think like that's a lot of analysis required for a building, but these days we are very lucky to have a lot of different softwares that can help us to design, to analyze and design building structure, any sort of structures. The most common softwares that are used are StatPro, SAP 2000, ETAPS, and Robot. Autodesk Robot is also used in some companies. The advantages of using a software is it provides you greater efficiency, more power in terms of calculations for different analyses, such as matrix methods or nonlinear analysis. And then you also have the code support. So when you have a software open, then when you are going to design, then you sort of pull the code that you are going to use. Let's say in standard code 875, then you have a lot of parameters already built in that software, which is very efficient and saves a lot of time. But the important thing to note here is that using a software would mean that you are going to trust yourself into something that you may or may not know. So you need to have some sort of finite element knowledge to use that software. And also sometimes it's very difficult to understand the errors inside the software. So you need to be very proficient in finding those errors and correcting yourselves. And there are a lot of default settings within the software that the software thinks is okay to do. But depending on your project or depending on your situation, that default setting might not be appropriate. So you have to figure out any parameters that you are going to use. And you also don't have to rely too much on the software. It's not a good thing to rely 100% of the software and trust it. You also have to do some manual hand calculations and compare your results with the software results. I've pulled out some snapshots of the CSI ETAP software. So when you have ETAP software, if you're going to do a seismic analysis, what you can find is you have a pre-built setting of a seismic load pattern, which you can apply loads on any directions. You have different zone factors inside the code, and so basically you just have to input few parameters. The software is then going to calculate your base shear depending on your period of the building and any sort of calculations that you may have to do. Similar for the wind load over here, you just have to specify your basic wind speed and terrain categories and class of the structure and things like that. And the software will automatically calculate your wind base shear and different forces that you maybe need to design your building for. So this is a very good tool to have, but also you need to have control over your tools, and you need to understand how you are going to compare the software results with the manual calculations. And the new evolutions and innovations that has happened in seismic analysis and design. So to touch base on that, so when you have a building that we normally design, you have a fixed base. So there is your foundation in green, and then you have your building system at the top. So when a earthquake force occurs, the building shakes violently on the sides of the earthquake, and there's a large movement that we can see. So we are basically designing for this phenomena over here. But the latest technology that's sort of happening in different parts of the world is if you are designing something very critical or something very important building that has to be operational in the event of the earthquake, then what you have to do is you have to make that building earthquake proof, kind of earthquake proof. So what you have to do is separate the foundation and the building using some mechanism so that the building and the foundation doesn't vibrate together, and there is a lot less damage on the building. So basically you can imagine if you have some kind of a roller at the base of the building, when the force occurs at the ground level, the rollers will not impart force on the building at the top. So the building will not see the same amount of force that you'd see in a fixed base building. The force would be, let's say, 5 to 6 times lower when you have some sort of isolation mechanism. So this mechanism is generally known as base isolated system. You'll have a very high density lead or stainless steel plate, kind of rubber plates inserted on the base of the building that sort of absorbs all your force, so the building at the top doesn't suffer any damage. The figure over here shows that base isolation mechanism at the base of the building. So over the top you have your superstructure, and at the base foundation level you sort of provide these roller or isolation mechanism that sort of isolates your building from the earthquake force. Some other mechanisms used to treat the earthquakes are damping mechanisms. So when you are designing a steel frame building, you have all these cross braces and diagonal braces. And people have found out a way to separate your earthquake force, actually dissipate your earthquake force inside this brace with a friction as well as viscous damping mechanism. So when you have a friction damper, what it does is two surfaces of the metal are compacted within that brace. So when the earthquake tries to move that brace, the friction acts between them and it sort of dissipates the energy. Similar mechanism is available in terms of viscous damping. What you have is a very high density viscous fluid in a piston at the end of the braces, which sort of absorbs all your seismic force. So if you are going to pursue, or if you are trying to figure out whether structural engineering is a career path for you, sort of lay out what you would be doing on your day-to-day basis. So first you'll be involved in designing different types of structures. Mostly it will be buildings, bridges, hydropowers or dams sort of structures. Normally you'd be starting yourselves with the concept design of the structure, working with the choice of materials, whether you'll be using reinforced concrete or steel or any sort of other materials available to you. And then you'll be working with architects. If you are going to work in buildings, then you'll be working definitely with the architects, and architects are not taught well in earthquake analysis or design, so they know very little about these things. So you have to coordinate and communicate with architects to arrive at an optimum solution from the initial stage of design. So after you coordinated with architect to come up with the layout of the building that's workable, then you sort of go yourselves and try to analyze the structural members. You design your whole building for the lateral load systems as well as gravity load systems. And then you also go and design your individual elements, such as you design your slabs, you'll be designing your beams and columns and foundations. And you'll be also working with geotechnical engineers as well. You'll also be working with mechanical and electrical engineers as well in different buildings or any other structures. So a lot of coordination, interdisciplinary coordinations has to happen, which is also very challenging, as well as it also is very interesting. And then once you have designed your elements, you have to produce those designs in drawings or a model that has to go to site, and that thing has to be built, and then you'll be going to site and doing an inspection or drawings to communicate between your design and what is being constructed on site.